Okay, so we're going to be starting talking about something called summation notation, which is a type of notation we're going to be working with for the next couple sections. So this is summation notation. And what we get is if we have the sum of j equals m up to n of some aj. This is the starting value of the index, and we count up by ones till we get to the stopping value of the index. So we would start with a, and then j gets replaced with m. Then we add to it. The next term would be a m plus 1. So you add 1 to the subscript, and then you would add to it a m plus 2. And you keep counting up by these ones until you get all the way up to plus so forth, so on, till you get up to plus an. So a few examples. If, say, we had the sum of j equals, let's say, 3 up to 6 of j squared, that would be, you'd start at 3, so you'd get 3 squared, plus, then j is 4, so you get 4 squared, plus, then j would be 5, then j would be 6, and since 6 is a stopping number, we stop up there. So we just plug in for j each time with 3, 4, 5, and 6. So another example, and then you could total this out if you wanted to. You would, that would be 9 plus 16 plus 25 plus 36. And so this thing eventually does simplify down to just a single number for this example that we're doing here. So we'd have 9 plus 16 plus 25 plus 36. That would all total up to 86. So let's look at using this summation notation on one more thing before we start using formulas with it. So let's say we're looking at j equals 1 up to 4 of 3j minus 2. So j would start at 1. So we would start out with the first term being 3 times 1 minus 2. Then j would be 2, so we'd get 3 times 2 minus 2. Then it's 3, so 3 times 3 minus 2. And then the final last term, because that's the stopping number of the index, we get 4. 3 times 4 minus 2. So 3 times 1 is 3. 3 take away 2 is 1. Plus this would be 6 take away 2 is 4. Plus that would be 9 take away 2, which would be 7. Plus this would be 12 take away 2, which is 10. So we would get, let's see here, 1 plus 4 is 5. 5 plus 7 is 12. 12 plus 10 would be 22. So this series would total up to 22. Okay, so that's a little bit about how that notation works. There's a couple properties we want. So we get this linearity of summations. So we get a couple things here. If we have sum of j equals m up to n of a subscript j plus b subscript j, we're able to view these terms individually. So we can view this as the sum of j equals m up to n of just the aj plus the sum of j equals m up to n of just b subscript j. So you're able to take the series, the summation and series, and you're able to break it across. You're able to break it across the addition. Just like derivatives and integrals, if you have a constant, so c times some aj, you're able to push the constant out front of your summation. And so we get that would be c times a sub j. The final thing is if you have j equals 1 for this one, so we're starting our thing at 1 instead of m. If you have 1 up to n of k, this will equal k, so forth and so on, till you add it to itself n times. So this will equal n times k. Because when this is just a number, when j is 1, there's no place to plug in j, so you just get k plus, then j is 2, so you just get another k, plus j is 3, get another k, etc. And eventually we get our equation like that. So what we're going to do is we're going to write our down three formulas for what we call our right endpoint approximation. Which is going to be, we'll use Rn to represent the right endpoint approximation. This will be delta x sum of j equals 1 up to n f of a plus j delta x. So here's our formula for right endpoint approximation. We're going to put a formula down for left endpoint approximation and then one for midpoint approximation. So we get, for the left endpoint approximation, we get L subscript n. Sorry, there should be a capital N there. So L subscript n equals delta x sum of j equals, instead of starting at 1, we start at 0, and we go to n minus 1, f of a plus j delta x. Okay. And then finally we get an equation for our midpoint approximation. So in the midpoint approximation, we use the midpoint of the segment to set the height of each of those individual rectangles we were talking about. So for this one, we get j equals 1 up to n, f of a plus, it's going to be j minus a half. This is what drops you back in the midpoint, times delta x. That'd be our midpoint approximation equation. So we're going to do an example that has us find each of these approximations for a certain function, and then after that we'll probably pause part 2 there, and then we'll finish stuff up in the final section. So what we got here is, for this example too, I'm going to do it kind of similar to the textbook. I'm going to use the same function, but I'm going to change from R6, we're going to calculate R4, L4, and we're going to calculate M4 for f of x equals x to the negative 1. On the interval 2 up to 4. So for all of these, the delta x, you take, we're looking at 4 subintervals in each case. So to get delta x, we take the interval length, which is 4 minus 2. We divide it by how many subintervals we want. So that's going to be 2/4, which is 1/2. So delta x in this case is 1/2. When we want R4, this is going to equal delta x sum of j equals 1 up to 4 of f of a plus j delta x. So delta x is 1/2, so we're going to replace the delta x's here with 1/2. Okay. A is the left endpoint of the interval, so A is going to be 2. So I'm going to rewrite this, and then we'll plug into the x to the negative 1, and then we'll start seeing what our terms actually are. So we have 1/2 sum of j equals 1 up to 4, f of 2 plus j times 1/2. So this will equal 1/2, and I'm going to start evaluating the series at this point. So we get f of, okay, when j is 1, this will be 2 plus 1/2, which is 2.5. Plus, then when j is 2, this is 2 plus 2 times 1/2. 2 times 1/2 is 1, so this is 2 plus 1, so that'll be f of 3, When j is 3, this is 2 plus 3 halves. 3 halves is 1.5. 2 plus 1.5 is f of 3.5. And then when j is 4, half of 4 is 2. We get f of 2 plus 2, which would be f of 4. So this will equal 1/2. The function that we're dealing with is x to the negative 1. So it'll be 2.5 to the negative first plus 3 to the negative first plus 3.5 to the negative first plus 4 to the negative first. So when we do that, type that in my calculator. And we get, so we get this is about equal to 0.635. So that is our right endpoint approximation from 2 to 4 of the function 1 over x. What it actually looks like is the function 1 over x looks kind of like this. So what we're saying is from x equals 2 up to x equals 4, we got these 4 rectangles, and we're using the right endpoint of these rectangles to set the height of the function. So the first one starts here at 2.5. You'll go up, you'll hit the function, that'll set the height of your first rectangle. Then you go up, this would be 3, so you go up 3, hit there, come over, that's the height of the next one. Here, come over, that sets the height of the next one, and that sets the height of the final one. So we're actually kind of undercounting the function because all these little parts above these bars don't get counted. And what is the area of adding these 4 bars? Because f of 2.5 is the height of the first bar, and it gets multiplied by 1/2, which is the width of the first bar, so that's the area of the first bar. And that half distributes to all these terms, so you get basically, this is equivalent to adding up the area of these four bars of the function 1 over, or x to the negative 1. So that's the right endpoint approximation. Let's do the left endpoint approximation. That'd be L of n, delta x, series starts at j equals 0 up to 4. The left endpoint 1 doesn't stop at 4, it stops at 1 less, so it's going to be 0 up to 3. It'll be f of a plus j delta x again. Delta x's are 1/2. And then a is 2.
Winner is Duck 67, Margaret Pernington. Come on over and claim your prize.
So we're going to rewrite this a little bit nicer. We get 1/2 sum of j equals 0 up to 3, f of 2 plus j times 1/2. So we're going to kind of evaluate this out. We'll get 1/2 times, let's see, j starts at 0. When j is 0, this is 2 plus 0, which is just f of 2. Then j is 1, so we get 2 plus 1 1/2, which would be 2 plus 0.5. So that'll be f of 2.5. And then j is 2. 2 times 1/2 is 1, so 2 plus 1 is f of 3. And then we stop at j equals 3. That's 2 plus 3/2, which is 2 plus 1.5, which is f of 3.5. So we'll type that all in, or oops, we're not already typing it in yet. We need to evaluate the function at those points. So the function is x to the negative 1, so you'll get each of these values to the negative first power. And then that gets us a format we can type into a calculator, or we could work out by hand if we wanted to do it that way. And let's see what we get. And so we total that all up, we get 0.759, would be basically 0.760. So what this one looks like is we got our same type of curve here. Our 1 over x function from 2 up to 4 is kind of doing this deal. So here's 2, here's 4, here's 3, and the in-between. So this time at 2, we use that, and we let the left endpoint set the height of that rectangle. Then 2.5, the left endpoint there sets the height of that rectangle. 3 sets the height of the next rectangle. 3.5 sets the height of the final rectangle. And so your approximation looks like that, where now you're using these left endpoints to set the height of each rectangle. And we are slightly over where the previous approximation was under, because you could see it was skipping little parts underneath here. This one's over, so when you use the left endpoints, you are including little bits beyond the function. So this one will be over what the true area under the curve is. Final one we need to do is the midpoint mn equals delta x. Series of j equals 1 up to 4. Just kidding, we're not finding mn, we are finding m sub 4. So, finding that, it would be f of a plus, it would be j minus a half times delta x. So if we check here, again, it's delta x, j is 1 up to n, f of a plus j minus a half delta x. And this j minus a half term, this lets us center it, where instead of using the left or the right endpoint, we use the middle point of each bar to set the height of the bars. So delta x is still a half, a is still 2, because the left endpoint is still 2, delta x, delta x is still a half out here. So we'll get a half series or summation of j equals 1 up to 4, f of a plus j minus a half times delta x, which is a half. See, so this will be a half series of j equals 1 up to 4. Oops, and this should be, instead of a over there, that should be a 2. Okay, so we get f of, let's see here, when j is 1, 1 minus a half is a half times a half is a fourth. So we get 2 plus a fourth, which would be f of 2.25. Sorry, I'm writing this kind of badly. Oops. So we're trying to evaluate the series, so I don't need the series block here. Trying to evaluate it. So we got f of 2.25 from that. That was j equals 1. Then j is 2. 2 minus a half is 1 and a half, which we could say 1 and a half is 3 halves. 3 halves times 1 half is 3 fourths. 3 fourths is 0.75. So 2 plus 0.75 would be f of 2.75. Okay, then j is 2. Or 3, sorry, j is 3 next. 3 minus a half is 2.5, which is 5 halves. 5 halves plus a half. 5 halves times a half is 5 fourths. 5 fourths is 1.25 plus 2 is going to be f of 3.25. And then finally, j is 4. 4 minus a half is 3.5. 3.5 is 7 halves. 7 halves times 1 half is 7 fourths. 7 fourths is 1.75. 1.75 plus 2 is f of 3.75. So it should be 3.75. Okay, so we're going to evaluate those numbers by plugging them into the function. We get 2.25 to the negative 1 plus 2.75 to the negative 1 plus 3.25 to the negative 1 plus 3.75 to the negative 1. We'll total that all up in our calculator. Let's see, plus 2.75 to the power negative 1 plus 3.25 to the power negative 1 plus 3.75 to the power negative 1. And we get, this is about equal to 0.691. So what the midpoint approximation did, if we were looking at our function, like we've already calculated it, but if we just wanted to kind of recap and say like what did the rectangles that it produced, what did those rectangles kind of look like? You would say, all right, here's 2, here's 4, here's 3, and then here's 2.5 and 3.5. You use the middle to set the height of that first rectangle. So that first rectangle looks like this. So a little bit's below the function, a little bit's above the function. Then next was 2.75, which was here about. That sets the height on that rectangle. 3.25 is here. That sets the height on that rectangle. 3.75 is there. That sets the height on the final rectangle. So in this one, the points that we were hitting the function at are in the middle of each rectangle. For the left endpoint approximation, the points where you hit the function are the left endpoints of the blocks. And on the right endpoint approximation, the points where you hit the functions are at the right side of the blocks. So this is kind of right endpoint approximation, left endpoint approximation, and midpoint approximation. We can see they all give us slightly different numbers, and that has to do with, like in this one, we're undercounting a bit. This one's we're overcounting a bit. This one we're undercounting some and overcounting some, so that I guess net wise we're either undercounting or overcounting by a little bit, but it's slightly balanced itself out. And that's our example of calculating each of those expressions for left endpoint approximation, right endpoint approximation, and midpoint approximation of a function over a region. That's basically how it goes. So we're going to stop the second part here.